All right, what's up, my sexy people? So in today's video, we're gonna continue physics, but before we continue physics, last time we didn't have a standard mass or length or anything like that. I told you that I know that there's new units. That's the new scientific standard of basically humans. But since hold on, let me take a drink real quick. Okay, there you go. Sorry, my throat's a little rusty. All right, so so I'm gonna bring out my notepad, and we're gonna before we continue on with chapter 2, linear motion, we're gonna look at some new scientific units. I'm just gonna put them down, and then next time we'll solve it. No, it's not. It's hard to write with this stylus. Whatever. 8. And then the other one is 6.02 times 10 to the 26 hydrogens equals, oh, I'm just gonna leave it like that. Hey, yo, Atkins, what's up, G? Thank you for stopping by. Today we're gonna be doing some physics. Only equals 1 kilogram. Yeah. All right. So let me put what these equal, and then this is 1 centimeter. All right. All right. So those are the standard units that I'm gonna use for the rest of the book. So whenever I talk about 1 centimeter, we're talking about uh, 1.35 times 10 to the 8 hydrogen bonds. And when I talk about kilograms, I'm talking about 6.02 times 10 to the 26 hydrogens. All right. And that equals 1 kilogram. All right. But, anyways, let's continue on with the book. Oh, wait. Before we continue on with the book, I got some these are my notes from back then, and it's actually really important. I just don't know how I'm gonna do this. All right, so I don't know how I'm gonna do this shit. All right, man. Hopefully, I don't embarrass myself. All right. Uh, one thing is gaining a perspective in the universe. All right, so we all know about XYZ graphs. All right, so let's say this is the X, right, and then this is the Y. Right, and then there's also Z that goes right through the middle. Right, you see that shit? So this is basically three-dimensional space, basically, right? And uh I'm gonna okay, so there's three-dimensional space, right? And then to solve everything, right? Everything in the universe, it's either physics, right? Shit that we could actually see, and then chemistry, right? And this is not found in any textbook anywhere. So what we're doing is something different. I'm just trying to show you a different perspective of the universe, all right? And then there's shit in between that's both physics and chemistry. All right. You see that? And then uh okay. Okay, but basically just think of that, right? Now let's go back to our graph. All right. So everything we see, oh shit. Let me paste that shit. All right, so everything we see, right? I'm gonna erase this. Or actually, let me leave it on. All right, so everything we see, right? It's either shit that we see in real life, right? We'll call that a plus, right? And uh, okay, hold on. Let me something went in my eye real quick. Okay, there you go. All right, so this is shit we see in real life. All right, we'll call it plus plus. So let's say this is uh three three pi. Like we're looking at everything in terms of 3 pi r squared over 4. Okay, so this is everything we see. All right, so imagine this is like the people. So this is shit that we see in real life. All right, everything everything that we see in real life, right? And then we'll call this the physics side. All right, we'll call this physics, right? So this is the physics side. And then over here, we're gonna call this. You see over here, the where the negative is, right? The double negatives. All right. We'll call this. We'll call this chemistry. And what's an example of over here? This is the like a normal force. We'll discuss what a normal force is. There's a normal force, magnetism. I know the fucking physicists are gonna be pissed. All right, so the magnetism, but fuck them, right? So this is shit that we don't see, but it involves chemicals or something in magnets, right? And what's a magnet made out of? Some chemistry, right? Some kind of chemicals, right? So that's shit that we don't see, but that exists in real life, right? Okay. So those are examples, okay? So let me clear everything out. Okay. So we got that. This is the physics side, shit we see in real life. And right here's the chemistry side, shit we don't see, but it's definitely real in real life that we could see, right? This is plus plus, right? All right, but then you got a quadrant over here, and let's say what's something that's uh what do you call it? Something that involves chemistry, right? Plus physics, right? An example of this would be friction. So if you fall your ass down, when you scrape yourself, the molecules what want to attract to each other and bond, right? Or if you're on ice, there's less, let's say it's less slippery. So let's just say that's friction. Just give you an example. All right. But then you have over here like a plus and a minus, right? I'm just showing you something. So let's say this is physics with chemistry, right? An example of this would be like gravity. Okay. So uh you always feel gravity, like you always feel something, an acceleration, right? You always feel an acceleration. You don't know why, but you're always accelerating down, and you know it's because of the material that's beneath you. Okay, so just give you guys an example of how to look at the universe. Okay, this is just a graph showing you how to look at the universe. So if you're looking at it carefully, imagine you're looking at everything as a volume of a sphere. Okay, and in it, all these things that I just showed you are happening. Okay, you see that? Hold on, guys. Let me wash out my eye real quick. All right, there you go. All right, I will show you my notes, but I can't show you my notes because we can't get too ahead of ourselves. All right, so you see that? So now you're basically all the forces of physics and chemistry are happening like in a three-dimensional space. You see that? You have the XYZ. Oh man, guys, I'm trying to pay attention. Who the hell is outside? All right, so you got the XYZ axis. You see that? All right, so what does that mean? Okay, so if we go back to our graph, okay, everything that's happening in the universe, all right, I'm gonna build you up to the simple building blocks, okay. All right, where do I want you at? All right, so everything in the universe is made up of either mass, oh shit, mass or energy, right? And everything is always moving, so everything's always accelerating. Okay, right? So everything's always accelerating. Okay, and you could accelerate in every direction in the XYZ axis. Okay, in any direction. Okay, you see that? So you see what I'm doing? So if you're a particle right here, right? And let's say there's a magnet right here, or no, let's not even say that. If there's a particle right there, you're existing in this you're existing somewhere in the universe, and no matter what, you have an XYZ, right? You have some kind of direction, right? In the form of XYZ. You see that? Okay. And then all right. And then let's say let's say you combine uh all the physics stuff. We're gonna put it on one side. All right. And this is shit that we see in real life. Let's say the the stuff that actually happens in real life, right? Right? All right. And then right here is going to be the physics plus the chemistry. And then over here is just going to be the chemistry shit. Okay. And then I want you to look at this as kinetic energy, like thing that's moving that we always see in real life, right? And then I want you to look at this as potential energy, right? Potential energy. And then this is non-conservative. Wait, hold on, guys. I got to call real quick. Hello? Oh, I'm doing a video real quick. But all right, my bad, everybody. All right, so this is non. Oh, this is non-conservative forces or not or non-conservative energy. I'm just gonna call it. Sorry, I'm so tired right now. I'm just gonna call it internal energy. Okay, see that? So I'm just gonna call that internal energy. Okay, there you go. All right, and then what else? Looking at my notes real quick. Okay, there you go. All right. All right. So we got that, right? And then from right there, and remember how I told you everything's either energy or mass, and everything's always accelerating. All right. And then it's always going in a certain direction. See that? Is equal to the mass. So mass and the energy of, uh, of all the potential energies, they're always accelerating. Okay, you see that? And they're always accelerating in a certain direction. And then this equals the internal energy that is mass is also a mass or energy, and it's accelerating. And I'm going to call that going in like that. Oh, actually, on this one, I did not put it like that. On my notes, I put it like that. Now I remember why. It's going like that. All right. So you see that? So this is what we're experiencing in real life, plus all the potential energy. So gravity, this shit, and that equals plus internal energies. So um energies, like how I just discussed earlier, energies inside, like say within like atoms and shit like that, internal energies, okay? No matter what, okay? So keep that in mind, all right? So now we're going to go and jump into the book, okay? So now we're going to go and solve everything in linear motion, and then just keep in mind everything that I just did right now, kind of. Sorry, guys. I'm so freaking tired. All right. I'm in a weird position. That's why. Okay, there you go. And I have to read all retarded. All right, so let's start off. So we live in a universe of motion. We are surrounded by speeding cars, scampering animals, and moving currents of air. Our planet is in motion as it spins on its axis and orbits the sun. Therefore, there is motion too within our bodies, including the pulsations of the heart and the flow of blood through the circulatory system. One of the principal tasks of physics is to describe motion in all its forms and its variety. And it is with the description of motion, a subject called kinematics, that we begin our study of physics. In general, objects can move all in three dimensions: forward, back, left, and right, and up and down. In this chapter, however, we will consider the comparatively straight line. There are many situations in nature and technology in which objects move very nearly along a straight line. An airliner accelerating down the runway before it takes off, a blood vessel moving along a capillary, or a rocket climbing upward from the launch pad, all in the concepts that we'll study in this chapter apply directly to motion in 2 or 3 dimensions, which we'll study in chapter 3. You'll use the idea of this standing them now will be an excellent investment for our future. Constant velocity means moving at a speedy. Oh, wait, hold on, guys. Forgot that the camera's not even pointing that way. Wait, hold up. Yeah, güey. ¿Entiendes, güey? No, güey. All right, fool, ahorita, let me just I gotta do this shit. Let me just bring up the notepad as we read too. Fuck it, you know what I mean? All right. So 2.2 constant velocity. Oh, yeah, we're gonna keep going because I feel like we haven't done shit. We got at least got to do some kind of numbers. Okay. Oh. All right. So constant velocity means moving at a steady speed in the same direction. Okay. So figure 2.1 shows objects in linear motion, 3 swimmers traveling down the lanes of a swimming pool. Their motion is particularly simple because each swimmer has a constant velocity. The swimmer speed stays the same and the swimmers always moves in the same direction. Let's look at this kind of motion more closely. Each swimmer, okay, fuck that. Ahorita encontré una película chingón, güey, también, güey. Ahorita la ponemos, güey. Let me just finish this. At least do some kind of math. When I get into the math, yeah. Coordinate displacement and average velocity to measure how fast and in what direction and an object such as a swimmer moves. We first need a way to measure the object's position in different times. We do this using a coordinate system as shown in figure 2.2a to identify and label positions. We use the symbol X to denote the position of objects given in time. The value of X can be positive or negative depending on whether the object is relative to an origin or reference. Basically, if it's going towards you or away from you, you put a plus or a minus. Position we take to be at X equals 0. We choose that reference position to be anywhere that is convenient. For example, we might choose X to be at the point where we are sitting alongside a swimming pool. If our seat is 10 meters for short from one end of the swimming pool to the length of 50 meters, then we end of one pool is at X equals minus 10 meters and the other is at X equals plus 40 meters. Basically, hey, Rainer, what's up, G? We're doing some physics right now. All right, so basically, what that fucker? Oh, this is not the right thing. sorry. What the book's basically saying is, let's say it doesn't matter the situation, right? Hold on. You know what? Let's say someone's diving right here. Right? And then right here's the water. Right? It doesn't matter if you choose. Sorry, let me grab. Doesn't matter if you choose where to put the 0. Let's say. No, that's a bad idea right there. Let's say it doesn't matter if you say this is 0, and then when she jumps down, she fell down minus 10 meters, right? Or whatever. Or you could say 0's down here and she's up 10 meters. You see that? So it doesn't matter how you draw the perspective. What matters is that you know the perspective. You label your perspectives right. That's all it's really trying to say. All right. So, anyways, let's keep going. Uh, the coordinate, the coordinate or position of an object relative to the origin as what we call vector quantities. Vector are special quantities that contain two kinds of information: uh, size or magnitude, and direction. For instance, if we ask a person location of the origin uh, in or magnitude and direction. For instance, if you ask a person located in the origin in figure 2.2 where near the end of the swimming pool is, the answer of 10 meters is not very helpful. If you wanted to walk to the end of the pool, we would also need to know which direction to walk. The magnitude of the position of the end of the pool is relative to the origin is 10 meters. The direction of the end of the pool is specified the specified by the relative to the origin of 10 meters. Oh, minus sign and the coordinate system, which is what we use x equals minus 10 to fully describe the position of the end of the pool. The position of the end of the pool is relative to the. Okay. I think this is the example that we're trying to do the whole time. But I mean, we don't care about the graphs right now. We're just reading until we get to the numbers. All right. The origin is 40 meters in direction. X equals plus 40 for the motion of a straight line. And the direction is always given by the sign of the quantity. All right. So basically what it's saying, let's say the swimming pool's right here, right? And then let's call this 0. X and Y, right? So let's say this is the 0, right? What they're trying to say is you got let's say this is 5 meters. Oh shit. Right? So it doesn't matter the direction, but what they're trying to say is you got to label if you call one side, let's say this is you call this side the positive, this side has to be the negative, okay? But if you label it in physics, if you label as long as you label it right, you could call this the positive and call this the negative side. As long as you labeled it correctly, that it's right because even if you say, "Oh, I moved negative 10 meters," but either way, we know it's this way. You know what I mean? As long as you know, as long as you labeled your shit right, that's all they're trying to say. All right, let's keep going. Let me see how far I have to go. Yeah, this might take a while. So I think we might just read this last shit and then we might end it pretty soon, actually. Or, oh no, let's see. All right. Okay, the positive value displacement means her value of the x increase. We say that that she moved 50 meters to the positive x direction. By comparison, swimmer B figures some shit, travels in the length of the pool in the opposite direction for the limit x equals plus 40 meters and all that. Okay, we don't need that. Note that the displacement of either swimmer does not depend on the choice of the reference position at figure 2.2b. As an example, we choose x equals 0 to be at the left hand end of the pool and the right end of the pool, x equals 50 meters, and a displacement of a swimming pool. Wait. Of the swimmer A x equals 2, x equals 1 at 50 meters, and 50 meters is increased, so we choose x equals 0 to be the right hand at the end of the pool. the left hand end, x equals minus 50. Oh shit. Sorry, my camera went down. I'm very busy, bro, but I'll come back and rewatch it, my G. All right, thank you, bro. Then I definitely got to keep going then until we start getting to the real math. All right. You know what? Fuck all this shit. Let's just get to the math. Right where right there. Cause it gets pretty fucking boring reading that shit. And really the math is the most important thing. All right, there you go. All right, so velocity. What is velocity? All right, so velocity is basically speed, right? Speed. So there's different equations you guys gotta know. Equals distance divided by time. And velocity, the difference between speed and velocity is velocity has a direction. So I'm gonna put a squiggly arrow. See, it has a direction. See that? Velocity, right? Look at that. I just did the fucking equation right there without really trying. All right. So we just solved all that shit just by writing that. All right. So anyways, going back to the other equation, remember I have the mass and an acceleration. So we have mass and an acceleration at a certain angle, right? Or a certain direction. And what is acceleration? If you look at acceleration is if you have a velocity, right? So you have velocity and then you travel, let's say you speed up or you slow down, right? Let me break down what acceleration equals. All right. So let's say you're at 0 and you speed up to 5 miles an hour. All right. You see that? This is time 2, time 1. Okay. So an acceleration is exactly that. It's either a change in angle. Oh, I forgot to say that shit too. All right. T2 and T1. See that? All right. All right. So that's an acceleration, right? So you go to, it's either a change in speed or a change in angle is an acceleration. Okay. But why is that important? Okay. So that equals an acceleration, right? All right. That's an acceleration. But if we want to break down but I'm just trying to show you trying to break down to the equation that we see right there on the book. All right. So you got velocity, right? So that's an acceleration is equal to that. You see that? But now we're going to break this down. What the fuck is a velocity? Velocity is equal to distance divided by time in a certain direction. You see that? That's what velocity is. Speed is equal to the same shit, distance divided by time minus the direction. See that? That's what speed is. Some people might be like, oh, speed is also a drug. All right, there you go. But that's what speed is. And that's what you see right there in the book. You see right here where it says velocity is equal to distance times the time interval minus it didn't have the direction. All right. But velocity, distance, time interval, and that shit. And you can solve things. Okay. We don't even need to read the book. We could just keep reading the equations and you should be able to read the book. But since we're doing this, we're going to be reading the book, I guess. Because that's what we've been doing with the chemistry book. But just know we don't. Actually, let me have that shit up. But just let you know, you don't really need that shit. All right. I mean, we don't really need read the book, but I recommend it. All right. So note that the average speed does not contain a direction information. The average speed is both swimmers is positive number independent of the direction they swim. To get direction information, we need to calculate the average velocity of the object, which is the vector quantity. We use the symbol V average X for velocity. This symbol is very close to the symbol used to denote the average speed, but it includes the subscript X to remind us that the object is moving in either the positive or negative X direction. The average velocity is given by the displacement divided by the time interval required for the displacement to occur. Consider swimmer A again, who starts at position X equals minus 10 meters. At the end of the position, X equals plus 40 meters in 25 seconds. Her average velocity is then okay. There you go. So distance, we just basically solved the equation already. All right. You know what? Let me write over this one. Uh, uh, uh. All right. I don't know how, but okay. So you see, let's clear it up. V is equal to distance divided by time, right? So all they're doing is getting two points of reference. So from point A to point B, right? So all they're doing is getting position 1 or position 2. You see that? And position 1. So let's say this is 1 and this is 2. Okay? And they're getting the average distance and the time that it took you to get there. All right. And then remember, everything's an extension of the mass of the forces. Okay. A force of this equation that we first originally started. Okay. So we went from talking about acceleration to velocity to velocity to the average velocity right here. See that? To where we are right here on the book. See that? That's what's going on. And all that means the average of two different, let's say how long it took you to go from point A to point B. That's all this talking about. I forgot where we're at. I think we already. Well, I think we already did that shit. All right. So now, all right, let's go. So the swimmer A moves at the positive X direction shown in the positive sign of the average or the left. The average speed equals 2 meters per second. Some common objects of both quantities. All right, we don't need to really do all that shit. All right, let's flip the book. Okay, now, okay, you see this concept? They're just calling it delta. This is their symbol for delta or change. When they see a delta, it just means of change. So let's look at closely at the equation right there. All we're doing is figuring out how they solve their equations, how they're getting the equations. Okay, that's all we're doing. Okay, so on the book where it says velocity average, I'm just gonna say AV because it looks kind of, oh fuck that. I don't know if I could write with this. Okay, velocity average is equal to, yeah, this is hard to write. Remember the change in two different positions, right? So I'm gonna draw an object there. Oh shit. Right? And let's say it's traveling this way. See that? And this is the time. See that actually they might say, oh no, that's right. That's right. Yeah. See that? So this is, so let me label this 2 and then this part 1. So 1 is where it originally was and 2 is where it's at right now, okay? That rock right there that I just threw. So imagine I'm right here and I just fucking threw that rock right there. See that? And I just threw that rock. All right. And that is called change in X or delta X or delta time. All right. So when you see a delta, that's a delta sign, which means change. So we're just talking in terms of the way the book talks. So when I say delta, all it really means is the difference in the time. So let's say it took you 3 seconds. Right here, you add 3 seconds, and uh, and then over here, you started at 0 seconds. See that? So when you subtract 3 minus 0, no matter what, it's going to be a positive number. That's why they put a 2 in the front. Okay? Or position 2 first. So it's always a positive number. Okay? So you could swap it the other way, and but you're going to have a different sign. Instead, you're going to have a negative. Okay? But people don't like to deal with the negatives because it might throw them off. So that's why they put a T minus 2 first rather than a T minus 1. But it means the same shit. Okay. But you might have a different sign though. Okay. But anyways, that's how you got that equation that's right there on the book right here. Okay. That's that equation right there. And I said all this extends from a mass, which in this case, oh shit, I'm erasing. Mass and acceleration at a certain direction. See that? So the mass in this case is this rock and it's accelerating forward at a certain velocity. Okay. And at a certain angle. Okay. So all this shit is extending from that A right here. See that? Okay. So let's keep going. All right. An equation, delta X is abbreviated for the change X2 or position 2 minus position 1 in the position X, and delta T is abbreviated for the change in time 2 minus time 1, that is the elapsed time. Throughout the study of physics, we'll use the symbol delta to represent the change of a quantity. Hey, Sinaloa es mío. Thank you for joining. Like I said, I'm gonna show you guys physics, and you guys don't need to do the work. But we gotta give a shout outs to SF Benny the Cali. that dude's a pretty smart dude. He knows physics also. But I was hoping he would be on the live, but I know everybody's busy. All right. We've calculated the average velocity of each swimmer's entire trip from one end of the pool to the other, but we can also calculate the average velocity of the segment of a swimmer's trip between the two ends. A swimmer has constant velocity if the average velocity is calculated for any segment of the trip has the same value for the other. All right. So segment as an example, 2.3, a swimmer A is at x1 equals 0 meters, and t2 equals 5 seconds, and at t2 30 meters, at t2 20 seconds. Her average velocity for her part of motion is let's see, average velocity. So basically using the equation we're seeing right there, number x2 minus x1 or T2 minus T1. They're just plugging in the numbers. So she's at 30 meters minus at 0 meters when she started, and she started at 20 seconds. Actually, she ended up in 20 seconds minus the 5 seconds initial. So it's going to be 30 minus 15, which should be 2. For whatever reason, I'm getting 2 meters or 2. Oh yeah, see, that's the answer. There you go. You see that equals 2. You see that? See, I'm just solving the equation just by ourselves, and then we're referencing the book. And look, you see that? That's what they got also. So when you're studying physics, that's the best way to do it, because in real life, when we're doing like the salt water and all that bullshit in real life, when you're doing shit in real life, you don't get these pretty fucking numbers. Okay, you're not gonna get a 30 and a 15 divided like that. You may get a 29.76543. I mean, whenever you see the Olympic fuckers, do you ever see any of them finish in like a perfect let's say the random the mile in 3 minutes? You never seen anybody put 3.00. It'll be like 3.5 something something. You get what I'm saying? Aquatic, thank you, bro. Man, thank you guys for being here, honestly. The clown trigger Rainer. All right, so man, I don't really feel like reading this shit. All right, fuck it. We at least did some math, right? I'm just trying to decide where we're gonna stop. Okay, we'll stop right here when we get to the first problem in 2.3. So we just got to be reading. So let's just keep reading, because most of it's just reading. Physics, when you're reading a physics book and you see nothing but words, just call that shit heaven, guys, because eventually you're not gonna have no fucking words in the book. You're just gonna see numbers, and you better know what the fuck you're doing. But that's why you're right here with me, because I'm gonna go over every single thing that's going on. I had a nitro trigger. It was dope. Oh, bro, I had one too. I had one in my reef, but I think I really like the clown trigger and the huma humas. But I only had the nitro trigger in my reef though. All right. That's the same as we calculated above. The entire trip from one end of the pool to the other. The average velocity is the value for the segments that we call simply the velocity to give it the symbol Vx. V minus X shows how to depict a swimmer as an entire motion in a way in which it makes it clear that the velocity is consistent. We draw a dot to represent her position equal time. Interval says t equals 0, t equals 5. Sorry. I'm going to say time equals 0, time equals 5 seconds, time equals 10 seconds, time equals 15 seconds, and so on. Taken together, those dots make up motion diagram. The spacing between the object, the adjacent dot shows the distance that the object traveled during the corresponding time interval. The spacing is the same between any two adjacent dots in figure 2.3, which tells you that the swimmer A traveled equal distance in the x direction and minus, that is, in the equal displacement on the equal time intervals. That just shows it meant saying the swimmer A has constant velocity. So what the fuck am I reading? So it's basically saying no matter what, it's going in 2 meters in the x direction and in the y direction. So basically it's going back and forth in the swimming pool. You see that? So let's call this plus and minus. That's all it's saying. It's going equally spaced and all that shit. Okay, that's all it's saying. All right. Yeah, another useful way to depict motion in terms of a graph of position versus time, also known as the xt graph, or in figure 2.4, we've turned swimmers A's motion diagram on the side, so the x-axis now runs upward. Then to emphasize that each by the amount that corresponding to the value of t, we add a horizontal axis for time to make it easy to read value of t that corresponds to each dot. The results of the graph of the swimmer coordinate x versus time t, or distance x versus the time t. There you go. That's more correct. Distance x, which is mentioned earlier, so that is called an distance x time graph. To finish the graph, we draw the smooth and curve connecting the dots for this constant velocity motion. The graph is the straight line. All right, let's just look at what we're looking at. All those words just for all that shit. Okay, it'll be easier just to look at the words and know what the fuck. I mean, look at the drawing and know what the fuck they're talking about. But they're talking about the spacing between these dots. See that? But anyways, let's flip the page because it's the last page, and then we're gonna head out. All right, figure 2.4b shows x, distance x and time graph for swimmer B. The swimmer also has a constant velocity, and the t graph is again a straight line. However, this graph differs from the x-axis and the slope of the line, how steep it is, whether it slopes up or down. Position x on the object time t, which is given in the symbol t equals 0. I mean x equals 0. If the motion starts at t equals 0, then x equals 0 represents the initial position of the object. So the slope of the line tells you that something equal to important the value. Object velocity, if you consider the position on the line, corresponds to time t equals 1, t equals 0, the x equals 1, x equals 2. The slope of the vertical line refers to x2 minus x1. Between those 2 points, the rise of the graph divided by the horizontal refers to time t2 minus t1 from the run of the graph, but then just definition, the average velocity equation 2.1 xt equals some shit. All right, let's just look at what the fuck they're doing. All right, let me just finish reading, and then I'm gonna show you guys this equation that they got right there. All right, slope, which means swimmer A is moving rapidly. The slope upward, which means she is moving in the positive x direction. By contrast, the x minus t graph in figure 2b also shallow slope swimmer B swimming some shit. Okay, the equation for constant velocity linear motion. We can write a simple and useful equation for constant velocity motion by staring with equation 2.1 v average equals x x2 minus x1 divided by t2 minus t1. Since the velocity is constant, we replace v average with vx. We choose either time t1 in this equation to be t equals 0 and use x0 instead of x1 and the symbol in the object's position at the time. We also use the symbol t and x instead of t2 instead of t2 and x2 to represent the later time and the object's position at the time. Then equation 1 becomes we multiply both sides of the equation by t and add x0 to both sides. The result is okay. So taking the equation, remember how I put x2 minus x1 and then t2 minus t1, right? So in physics, let's call this time equals 0 and position number 0, okay? So now let's rephrase it as x2 minus x0. See that? Over t2 minus t0. You see that? Okay. And then from that, okay, we got that, right? And then all that shit equals, let's say all this. Damn. The velocity, right? Equals velocity, right? So velocity equals this shit, right? Do you guys see that? Hold on, guys. I'm trying to see this real quick. Oh yeah. I'm right. I'm just tripping out. Okay. So equals velocity, right? So I'm gonna write this. So velocity is equal to I'm gonna write all this shit again. All right. So V oh shit, not V. Is equal to x2 minus x0. I'm gonna put parentheses on it so we don't lose track of it, okay? Over the time difference, all right? So I'm just gonna put time right there, okay? You see that? You could even call it you know what? So since we don't lose track of it, I'm just gonna call it T2 minus T0. Okay, so you don't lose track of it, okay? All this shit equals 0. Okay, you see that? But now I'm gonna multiply the time. Okay. You see that? So now I'm gonna multiply the time. You see that? Okay. So I'm gonna get the new equation is gonna be how did they write it? Okay, so the new equation is going to be V times T2 minus T1. See that is equal to uh X2 minus X0. Okay, you see that? You see that, guys? So let's clear it up. You see now we got this equation. You see that? But if you look at the book, we're still not fucking there. You see that? We're still not there. You see how we're still not there in the book? So the reason we're not there is because now we got to solve for this number right here. You see that? So to solve from that, now let's remove the parentheses. Let's remove the parentheses. Oh shit. I can't clear it up. Oh, I guess I have to do it over here. So let's clear out the parentheses, okay? There you go. So I cleared out the parentheses. You see that? So to solve for shit. I pressed the wrong fucking thing. Sorry guys, we had to watch this stupid commercial shit. I wonder if I have to watch this whole thing, dude. Come on. Which one was I using? What the fuck? What happened in my notes? Wait, hold on, guys. Okay, we got our notes back. Okay, so now we want to solve for this equation for this number. You see that for this number? So how do we solve for that? We add plus x, the initial x, okay? The initial position of the rock. So remember we threw the rock. So oh shit. So there's a rock, right? So here's this is the initial position right here. This is the initial position. Okay? So what we want to do is move the initial position to the other side. All right. So add it over here plus but first let's do a bracket right here so we don't lose track of this number. Plus 0. I mean plus the x 0. See that? So now let's rewrite the equation again. So the equation, hold on, let me go over this again. Just so we could see it on the next slide. Okay. All right. So now let's rewrite the equation. So it's going to be, okay. So we added this shit to this side, right? So let me start off the equation with that. So x 0, initial x, right? It's a positive now. You see that? It's positive is equal to the number right here. This shit right here. And remember I put the bracket, so I'm just gonna did I put an equal sign? Oh shit. Oh, is equal to plus. Remember that this number is positive, right? Plus. Hold up. Yeah, plus, because you see how the initial number is a positive, not a negative right there. Plus that bracket right there. So it's gonna equal V and then T2 minus what was it? T1. Some shit like that. Close bracket. is equal to x. I'm gonna clear it. Okay, yeah, there you go. You see that? So then we got that equation right there, which is this one right here. Hey, but Henry, how the fuck is it? Is it that right there? So let's just rewrite it in a different way. All right. So let's get x2 is equal to x0 plus what does it say? V, and then times the delta t. They just put t right there. And then you get this equation that they got right there. You see that? Bam. And then that says, okay, so that's how you calculate the falling object, okay? And remember, all this shit is extending from that mass and acceleration at a certain angle, okay? Remember that shit, okay? This equation gives the position x of the object as a function of time t. In the following section, we'll see how the equation 2.2 to solve problems at the linear motion with constant velocity. But even with this equation, an essential part of solving any such problem is drawing a distance x and time graph like those shown in figure 2 point some shit. Okay, and then there's just some other graphs right there, just so you guys can see it. Let me erase let me get that out of the way so you guys can see closer. But let's flip the page. All right, this is where we're at now. This is where we're gonna stop, guys, because I'm tired. We've been at this for an hour, and shit's just about to get good, but I gotta go though. All right, we're gonna finish right there. Solving straight linear line motion problems, and we're gonna use this equation that we just solved right there. Okay, so just remember this equation, okay, guys? And all this is derived from that. So this is the slide we're gonna leave it on, and we're out of here, guys. But much love for everybody joining me. But this is physics, and I know we just made some equation, and I know I kind of went through it fast, but all this, like I said, just rewind this, but all this extending from the acceleration value from right here, you get all this shit right here, okay? Okay. And acceleration is changes in velocity in 2 different points of time, okay? But that's how we got there. And now we're at 2.3, and we're going to end it there. Much love to everybody who joined in, and I'll see you guys on the next video. Aquatic Amigo, Sinaloa, Rainer, thank you for joining, bro. Much love. And whoever's watching right now, Atkins also, bro, thank you for joining. Much love to everybody that tapped in. I'll see you guys on the next live. All right, see ya.